hope that everyone is staying safe and as well during these weird times. I'm Noah Williams. I'm an undergraduate studying chemistry, and the research entitled here is Multilayered Hydrogel as a Skin Phantom for Jet Injections. This is just a quick outline of everything that I'm going to be presenting to you. We're going to start with a brief introduction of the material that we study, why we study it, and its importance in application. Then we'll describe some of the experiments that we are currently doing, and then we'll finish off with some future prospects we have planned for our research. Let's begin. In our research, we are currently doing a lot of study on hydrogel polymers. You can see some of these gels here. They're this yellow jello-like substrates in this transparent container. The plastic that you see on the top is a parafilm covering the gel. So hydrogels are a viscoelastic material that mimic the behavior of skin when we exert them in needle-free jet injections. Jet injections are currently the leading alternative to needle-free transdermal drug delivery. However, to optimize the performance of these needle-free jet injections, we need to study how the jet injectors disperse the drug in the skin. But we cannot use human skin in a laboratory setting, mainly because it's not readily available and it's very expensive to obtain, so it becomes very difficult to perform these jet injection experiments with real skin. So in our research, we study the mechanical properties of our gels, because if we can match the mechanical properties of skin to the mechanical properties of our gels, then the gels will be a great substitute to study drug delivery and even other experiments. So looking at the figure here in the top right, we can see that skin has three main layers. At the top you have the thin layered epidermis, in the middle you have the thick layered dermis layer, and at the bottom you have the large fat layer called the hypodermis, or even the subcutaneous layer. So each one of these layers has its own unique mechanical properties that affect the dispersion of an injection. So what we do is we perform injections through our hydrogels, and so we got a picture of that here below that same figure. And so you can see one of the gels that has been injected with dye. So when these gels are injected, the penetration of this injection creates cracks or channels throughout the gel. And in these cracks and channels, the dye goes into those cracks and channels, and it kind of creates these ball-like structures. So looking at the figure, you can kind of see these circular regions that surround the main line of the injection. So those are the cracks and channels that the dye is going into and kind of dispersing into a very circular fashion. One thing that I wanted to know is that during this presentation, I'll discuss gels based on their concentration, and we can express the concentration of gels by percent weight by weight. For example, if I say a 5% concentrated gel, that is 5 grams of gel powder per 100 grams of solution. So this is just a quick overview of how we set up our jet injection experiment. We start with setting up our gel under the jet injector. And so you can see that here with these three shades of yellow. One's brown, it's kind of white and yellow. So that's a multi-layered gel that we'll kind of discuss later. So we set that up under our jet injector, and then we will fill the jet injector with this blue dye. And then we kind of tie down this jet injector with brackets and screws, because when we fire it off, we don't want it to kind of ricochet or move around. So we really need to tie it down. And so the trigger, which is this yellow rectangle represented in the diagram, is how you set off the injector. So when we press the trigger down, the jet injector releases the dye at speeds of 100 to 250 meters per second. And while this is all happening, we have this high-speed camera that's capturing the video with 25,000 frames per second. So then we'll go back and we'll look at the video and we track the injection and we measure the depth at which the injection penetrated the gel. Then we'll go ahead and just kind of repeat this process with many different concentrations of gel, and then eventually we'll work our way up to the multi-layer gel. So these are the results of the penetration depth over time. So looking over here on the graph on the right, this is our log scale graph. And it shows the depth D of our injection over time T in milliseconds. And looking at the graph, we see initially it has a steep slope, high speed until at approximately 1 millisecond. At this point, the slope slows down. And so this happens because those ball-like structures begin to form that we were talking about before, how the penetration starts creating those cracks and channels, the dye goes into it, and it kind of disperses and makes these circular regions. And so these dispersions into those channels can actually increase the penetration depth, and we see an example of that in the 4% and 5% concentrated gel. So looking at the blue line and the purple line, we can see that slope kind of picks up and it begins to be in the same steepness as it initially was, you know, going from 0 to a millisecond, then past a millisecond, it kind of has that same slope. And same with the 5%, but it is not as exaggerated because it's more stiff, it's more highly concentrated. But when you get to the 6% or 7% concentrated gel, and we look at the 1 millisecond mark, we can kind of see the slope slows down. So it no longer is as steep as it initially was, it actually is less steep. And so what that means is that these ball-like structures that are forming into those channels are helping with penetration, but at a very slow rate, not as fast as the 4% and 5%. And then finally, when we get to the 8%, 10%, and 12% concentrated gels, when those cracks form and the dispersion is going into it to create these ball-like patterns, it no longer is helping the injection further penetrate the gel. The gel is too stiff for the dispersion to go into the gel. So what you end up getting is we kind of just get this giant ball of dye in our gel. And so now looking at the graph on the left, we're going to call this our simple scale graph. So it's the same type of graph on the right side, but it's not in the logarithmic scale. And what this graph tells us is the approximate time interval the injection takes place. And in the case for all concentrations of gel at approximately 40 milliseconds, you can kind of see the slope of every single line flat out. So there's no motion at this point. So what we conclude from this is that all of our injections last about 40 milliseconds, and that's when no more penetration will occur. So in the previous slide, we talked about the depth changing as the injection is occurring over time. In this slide, I'm going to discuss the final depth of the injection for each concentration of gel. So it's the depth measured at the end of each injection. This left picture here is a model of the final depth of injections for each concentration of gel tested. So this is what the injection looks like at the end of each test that we do. So we took a picture of each injection and we, at a bunch of different concentrations, and we placed them side by side. So when we look at it, we can see the difference of depth between each penetration. So what we can see is that with lower concentrations, there's a lot more penetration depth. And then as we increase the concentration, the final depth of penetration just begins to decrease. And so looking at the graph here on the right, we kind of plotted the results that we saw on the left. And so we have the final depth expressed as d sub f. It's measured in millimeters, and we are plotting it over increasing concentration of gel. And so again, as we can see, is that it shows that as concentration of gel increases, the final depth of the injection decreases. And this is because with higher concentrations of gel, the more stiff the gel is. And if the gel is more stiff, then the more resistant it will be to the penetration of the injection. Looking at the top of this of each bar in the graph, you see these error bars. So these error bars here are variations we had with each of the 6 trials that we performed on each gel. So after the injection is complete, we release the injector from the surface of the gel. So kind of looking back, if you remember from that diagram, we have the injector on top of the gel surface. And so when we release that injector from the gel, what ends up happening is that some of the dye that was injected seeps out from the hole that was initiated from the injector. So looking at the picture here on the bottom left, we see an injection that has been done in a gel, and it's represented in blue. That's the blue dye that was put in there. The white background is the internal gel compartment. So looking at the top, you kind of see this line, which is the path of where the injection took place. So if you look at the very top, where that line is coming from, that's where the injector was placed. So when we release that injector, looking at the picture of the right, we see that the dense liquid that was concentrated in that circular region really dims into a lighter shade of blue because the liquid is seeping out as a result from what we call elastic relaxation. So this graph over here on the right shows how much liquid dye comes out for each different concentration of gel. So on the y-axis, we have eta, which represents the percent of volume that is still present in the gel after elastic relaxation has occurred. And the x-axis is the different concentrations of gel that we tested. So for 4% concentrated gel, we see that it's marked at about 100% of volume. So that means that 100% of the volume was still encased inside the gel after we removed the injector and the elastic relaxation took place. So for the 12% concentrated gel, about 10% of the liquid was retained, meaning that 90% of the volume was squeezed out due to the elastic relaxation. So looking at the graph overall, we see that as we increase the concentration of gel, less liquid volume is retained in the gel. Or inversely, we can say that as we increase the concentration of gel, the more volume of liquid is lost due to elastic relaxation. So indentation experiments. So in our research, these indentation experiments are what we do on the gels to kind of determine the Young's modulus for our gels. So looking at the diagram here on the left, we have this blue figure, which is the translational stage. It's an automatic platform that moves up and down at speeds of 0.01 millimeters per second. It's a very slow process. And so the orange figure is the right angled bracket, and this just serves as a bridge to connect our translational stage to the loading cell. And the loading cell is probably the most important part of our apparatus here, because it contains the force sensor, and it also contains the spherical indenter. So zooming in on this spherical indenter here, you can see on this right diagram that we have a sphere that has a radius r. And so what happens is that when we perform this experiment under gel, the translational stage goes down and the spherical indenter is going to hit the gel, and it's actually going to indent the gel. So the spherical indenter is going to do this at a maximum of its radius. So if the radius is 1.5 millimeters, then the spherical indenter is going to indent our gel 1.5 millimeters. And while that's happening, the force sensor that's on the loading cell is going to measure the force applied to the gel as the spherical indenter is going inside. And so after it reaches a depth of 1.5 millimeters, which is the radius of the spherical indenter, it's going to retract. But when it retracts at the same speed that it did the indentation. So it'll retract at 0.01 millimeters per second. So looking at the results of the experimental indentations, we're going to look at the graph again at the right, and we can see this first line that's increasing. So like I said before, we are measuring the force as the penetration or depth of the indenter is reaching 1.5 millimeters. So at 1.5 millimeters, the indenter begins to retract at the same speed that it was indenting, which was 0.01 millimeters per second. So that starts creating this second line right next to it, to the right of the first line. And so we can see that the force applied to the gel decreases, as well as the depth of the indentation put on the gel. But when the spherical indenter fully retracts, we can see that the depth does not fully retract back to zero. This is because the gel is deformed from the indenter, so it will not go back to its original orientation. So what we do is this data is we take the first line, which is the slope made from the indentation, and we plot it on this left graph here. And so this left graph is the same as the right graph. It's the force measured over the depth, but we use what's called the Hertz equation. And the Hertz equation can be found just on the right side of this left graph. And so we use the Hertz equation to plot this black line, and we fit it to our experimental line. And so we use this to find E, which is Young's modulus. So to kind of go through Hertz equation real quick, E is Young's modulus, F is the force applied to the gel over depth, nu is Poisson's ratio, which is 0.5 for our gel, R is the radius of our spherical indenter, and D is the penetration depth of the indenter. So what we ended up finding for this 5% concentrated gel is that Young's modulus is 12 kilopascal. So it's important to note that this data is only for the 5% concentrated gel. We are currently still in the process of performing the indentation experiments for the other concentrations of gel. So using the high-speed cameras and a method of tracking the penetration depth for each injections, we can also track and outline the dispersion of our injections. So shown in this graph here is an injection that was done in an 8% concentrated gel. And the scale on the right side, towel, is the normalized scale of our time. So it's a scale from 0 to 1, 1 being the beginning of the injection and 0 is the end of the injection. At about 20% into the injection, looking at this orange tan line, we can see that we graph the radius at the bottom, x-axis, and on the left y-axis we have the depth. So we see this kind kind of central core of this forming ellipsoid. And what's interesting about this central core is that as the penetration or the injection continues, the liquid dye is going to continue to disperse around that central core. And so as the injection continues, the size of this circular ellipsoid is going to increase, as well as it's going to increase in its dark color. And so what's really important is how it increases in this dark color, because we're currently doing studies on how if we measure the amount of light that's transmitted through certain phases of this different shades of color, because it's getting darker over time, we'll be able to measure the width of the cracks that it's making inside our gel. So as I was discussing in previous slides, there's still some work to be done for the other concentrations of gel. And so, for example, we still need to finish determining its modulus for the other concentrations of gel, and we need to track the outline of liquid dispersion for the other concentrations of gel. But ultimately, what we're trying to do here is that we're going to take the results of our experiments and we're going to begin creating these multi-layered gels that are going to be used for our phantom for human skin. So there's a model that's placed here at the bottom, and so we can see that each layer is going to have a different concentration, and that concentration will be proportional to the mechanical properties of either the epidermis, the dermis, or the hypodermis layer. And then we'll just kind of vary the volume for the thickness to match the thickness of skin. I want to thank you guys for watching my presentation. I hope you all stay safe and stay well and be kind to one another. Bye-bye.